Hello.
Hello, aloha, as they say elsewhere in other parts of the planet. How are we doing, Conrad? You all right?
Very, very good. How are you?
Yeah, not too bad. It's just, oh my days, it's just been so much going on at the moment. Just when
Yeah,
there's 3 weeks to go and things are going to be dying down because of all my year 13s are gone, but then everything starts ramping up and you start wondering what on earth
yeah,
is going on. But there we go. So in terms of those pat tests your teacher mentioned, just so we can
yeah.
get that out of the way, those are essentially physics aptitude tests.
Mm,
Yeah. And
yeah.
only for candidates who are looking to go and study either natural sciences or physics at Oxford. Those are the entrance
Yes.
exams. But nonetheless, like I say, we have been doing more or less of that. I've been at times not telling you, but I've been mixing and matching some of the physics entrance exam questions.
Yeah.
But I've not called them that because otherwise it just puts an extra,
Mm,
cloud over the question and go, oh,
yeah.
wow, this is going to be very complex. So to remove that, I've not exactly given you the titles, but we do look at that. And to me, that would be very much one of the end games. I don't think you want to be solely using those for practice. You want to
Yes.
match. That's what it's all about.
Yeah.
Ultimately, what you want to refine is you want to make sure that you know the OCR examining board well, and you know how to give, I'd say, certain preconditioned responses they're looking for from definitions and such. And also, you want to get a feel for the style of the questions because they have a certain
Yeah.
style. So it's always good to make that your base. OCR has to be your base. You're allowed to venture out, get wings, fly away from base, and taste a little
Yeah.
bit of Pat, taste a little bit of Cambridge, but you still have to go back home,
Exactly.
which is the OCR syllabus.
Yeah.
Okay.
It's
Right.
yeah, because I've been sort of tasked
Yeah.
to sort of go off into the summer and basically come back to school with like a nice collection of sort of, you know,
Problems you've worked through.
work, yeah, prompts I worked through with,
Yeah.
marks in different color, just so I can show my teacher,
Yeah.
yeah, this is what I've done, give me an A star.
Yeah. Yeah.
That's
Absolutely. Absolutely.
so that's what I'm doing. That's what I'm, tasked
And
to
that's
do
what
now.
you're
So
focusing on to make sure that you can have that completed to a good standard, and then
yeah,
obviously, yeah, absolutely, and it has to be evidence based. Unfortunately, it has to
yeah,
be evidence based. They can't just take your word for it. And the thing is, even after
exactly.
you've come back with that, they will still hinge majority of the decisions on how you perform when you're back in school on the tests they give.
Yeah,
That will be the acid test for them.
exactly.
Because if you've got 100% in all the PAT tests, they were not there. They don't know what conditions you were doing those exercises in.
Yeah,
But the beauty about having a tutor is that the tutor can always give a second opinion as to what grade they think you are. And it's happened in the past before, not recently, but in the past years
yeah,
where I've had a student who I definitely can vouch to say this is an A/A star student, and the teachers
mm,
are predicting a C grade. And I've written a letter to say I have no idea where you're coming from, but when I do tutor
yeah,
this person, they do questions live in front of me, and that was a time before
yeah,
the pandemic had kicked in, so everything was one to one, and I'd go to the house, so I would actually see the student performing. It's not like now where
yeah,
we see you're working, and so things are a bit in a gray area where I'm like, okay, he's gotten to the answer, but I don't know how he's kind of made
yeah,
his way to that answer. It was a very different scenario, so I had to say, from my professional judgment, I disagree with
yeah,
the C grade that you've given him. He's definitely above a C grade. If you'd said a B,
exactly.
different. But in my books, he's definitely
Yeah,
A/A star. So that is the beauty of having a second professional opinion. And of course, because I'm not just a tutor, I'm also a teacher. It carries a
yeah,
lot of weight, because if I was just a tutor, then of course it means that I only know one facade of education, but
mm,
actually I've got a holistic
exactly.
understanding of how education works.
Yeah,
Righty. So importantly, important skills. We're going to call these skills. Mapping equations onto y equals mx plus c. It's a very important skill. But before we delve into this, let's just go through some basics first. Firstly, you are aware, and I'm hoping you appreciate, that this is the equation or general equation of a straight line?
Yeah.
Good. We need to have that understanding. And we appreciate that M represents the, what does it that represent?
The M, is that the gradient?
Correct, spot on. And what is X?
That's the variable on the x-axis. So
Yes, and the
just,
variable on the x-axis is rightly termed the independent variable.
yeah.
It's what we're changing. What is Y?
Just, you know, the same thing but on the y-axis.
Nearly there, and we call that
Nearly.
the dependent. That's
Right.
the dependent variable, the thing we're measuring.
Yeah.
Okay. And normally when you draw, if you're drawing up a table and it's some kind of practical activity, and you have to draw up a table, we always generally put our independent variable, which I'm going to call IV, in the left-hand column and the dependent variable in the right column.
Yeah.
That is the representation we use. So a bit like a coordinate system of X and Y in the second column.
Yes.
Also good. Now, what are the general type of equations or equations you shall encounter? What do they look like?
Normally it's a dependent variable. Can I give you maybe an example?
Yeah, actually more than an example. And this is where it's going to be a bit tricky for you because obviously you're doing maths, so you might not know the generic names. So you might end up giving specific examples, but I'll help you out on this front. So one of them is of course, in very simple terms, you're either going to have a linear equation or you will have a non-linear equation. So just for the next part, let's just put physics to one side and we're just going to deal with some maths. Yeah. And then we're going to see how that maths kind of relates to physics. Am I recording here? Yes, I am. Good. So a linear equation is generally an equation which, if plotted on a graph, will be a straight line. That's a linear. I didn't say directly proportional. I just said linear. It's a straight line. An equation that has a straight line of y versus x. Non-linear equations are ones that are not a straight line. They'll do all sorts of things. Now, some of them might do this. Now, this is what we call a reciprocal graph. Some of them might do this. We're going to draw it like this here, starting from there, from the axis, but never touching. So in this case, the reciprocal graph never touches the y-axis and it never touches the x-axis. You might want to make that point.
Yeah.
Here. Never touches either axis.
Is that in every case?
In every case. And a reciprocal graph is the graph you get from an equation that looks like 1 over x. In every case.
1 over x. Right, so that was what we were that was like the question.
Very good. You're beginning to tie them in. You're beginning to tie them in. Absolutely. But we're all going to bring it together. For now, let's just understand the different families of graphs we're going to get. This here is something known as an exponential decay. Now note it has a value on the y-axis, but never touches the x-axis. The reciprocal does not touch the y or the x. This here is an exponential decay. Key part is that it never touches the x-axis. So far, so good?
Yes.
So we've also got something known as exponential growth. Again, we're still looking at nonlinear. So exponential growth starts from 0 and it grows, and then there's some limiting value it never reaches. Just like how here, the limiting value is when x, or rather when y is 0, it never touches y equals 0. Here, it never touches some value of y. And it will all depend now on what the equation is. So this here is an example of exponential growth. So these equations here, you look at them in year 13. These have a relationship, okay, are related to e to the power of minus x. Is that relationship. This e represents what is known as Euler's number. You're going to encounter this. Euler's number should start with an e, and it's on your calculator, but we'll discuss this as and when we get to it. Okay?
Yeah.
This here has a relationship of 1 minus e to the minus x. So it's related to that. It's not the exact, that's what this little symbol means, that squiggly sign. It just says related to.
Yeah.
So the equation may be slightly different, but it's going to have this kind of stuff in there.
Yeah.
And then lastly, the last one which they want you to know, again, it's more year 13 based, is so-called the power law. So this deals with equations, in other words, which we can call exponents. These are equations that look like y is equal to a to the power of x. And what do these look like? They look like this. So they cut the y-axis at some value, and they grow exponentially very, very quickly. So that is the power law or exponents. Again, more the domain of year 13. So now that we've established the main family of equations we're going to encounter, now it's worth trying to see, well, how do these graphs actually appear? Or let's look at some examples of how they appear in some equations, okay? So we're going to primarily firstly deal with the reciprocal graph, because like I said, these are the domain of year 13, and we can look at them in more detail when we cross that bridge. Let's just have a look at how can we manipulate, if I insert a page here. So imagine, we're going to start off very simple. Let's imagine we have a drink of a nice one here. Resultant force is equal to mass times acceleration. So let's imagine I kept the resultant force constant. But I was changing the mass. So in other words, this here is my independent variable. That's what I'm changing in my experiment. I'm keeping the force constant. So what would this scenario look like? To be nice and easy. So imagine I had a table here and I had a trolley here and I had a pulley. And this is, and I remember I've said I'm keeping the resultant force constant. So I would have a constant mass attached. It would obviously have to be heavier than the pulley so that this thing can accelerate, but I'll be changing the number of blocks I put on top of the pulley and then measuring its acceleration. And I can measure that using light gates. Of course, I'd need two light gates, which can look at the velocity at 2 points and the time. So acceleration measured using light gates. And this we said is just a heavy mass. So this system can accelerate that way. Okay.
Yeah.
So we are changing the mass, we're keeping the resultant force the same. How? We're keeping that block that's accelerating the system the same. So we know the resultant force is the same. So the acceleration will be changing. So if I plotted a graph of, say here, remember that the independent variable is my mass. So if I plotted a graph of acceleration versus mass, what might that look like? Any ideas?
So would what would be on the y, and would acceleration be on the y?
Very good, because
axis?
it is my dependent variable.
Yeah.
It's what I'm measuring after I've changed the mass.
So would it be when mass is it, would it be a downwards, would it be a linear equation?
Now let's just look at this, the best way to try and think about this. So this here was said is constant. We're going to rearrange this equation, and now we can see this equation, if I wrote it in terms of a, because that's on my y-axis. So if I thought of this as y, and I want to write an equation that says y is equal to, yeah? In other words, a is equal to. How can you rearrange this equation in terms of a?
You would divide by m.
Correct.
Yeah.
Resultant force over the mass. Now note, this is constant. We said it's not changing.
Yeah.
Now this is where you now need to start creating patterns within your mind here to see how. Now, hopefully, if you look very carefully, and I help you see it if you can't see it, this is very similar to y equals to 1 over x. What is the pattern similarity? Well, both of them at the top have got a constant number.
Yeah.
Here, I've just called it, I could have called this 1 Newton if I wanted to. So now this would have been, I could have called the resultant force 1 Newton. So that would have been 1 over m. So note that this here, this equation is actually this reciprocal graph in disguise. So if I plot a against m, my graph will look like this, and it will not touch either end, either the y or the x-axis. So you literally absolutely need to know what this graph looks like. Unfortunately, there's no shortcuts more than to memorize it. If you want to, you can plug values in there. If you make x 0 here, what is 1 divided by 0?
1 divided by 0. 0?
Nope.
1 divided by
0 is undefined. It's impossible.
Yeah.
because
You
it's
get
impossible to
confused
find
as
something that
well.
you can multiply to 0 and get 1.
Yeah.
So there's no x value that this equation can satisfy. Likewise, there's no y value. So we know that if we plot a graph of acceleration against mass, that's what it would look like. And you can plug in values if you don't believe me. Just call the resultant force 1 Newton, change the mass from 0 all the way to 10, and you see that the acceleration will do that.
Yeah.
Good. Now, the next part to this is what they like. And I'm going to extend this idea a little. No, we'll extend, that will be another idea because it's a separate idea. I don't want to overload your brain right now. This is it's quite enough to overload a brain.
Yeah.
So we'll break it down. I've just thought let's best break it down, otherwise it'll get pretty confusing. Now, there's something I can do if I didn't want to get this kind of graph. It's not a very helpful graph for me. I could turn this into a straight line graph. What can I do to turn it into a straight line graph? Well, instead of plotting against m, this time around, I should plot acceleration against 1 over m.
Right. Yes. Okay, this is making more sense now.
Now, if I plot acceleration against 1 over m, I'm going to get a straight line.
Maths is very weird.
Why does it work? Okay, let's go back to y equals mx plus c, because that is the whole point of why we're doing this. We want to understand how mapping works. So here you have a formula that says A is equal to, can I use K for a constant for the resultant force?
If it's constant, then
Yeah,
sure.
Yeah, I'll use K. I could have used C, capital C, divided by M. But I know that if I plot A against M, I get this. So I'm going to plot A against 1 over M. How does that relate to a straight line? How does this suddenly change? Well, this is where you need to now be very super observant. K over M is the same as K multiplied by 1 over M. Are you following?
Yes.
It is. Now, if on your x-axis you plot 1 over m, it means that the gradient of the graph now represents this resultant force. You map it. This is my x term, 1 over m. Now I map this to k. So the gradient will represent my resultant force. There's no term here to map to C. So this means that this graph will pass through the origin, because it means that the constant or the intercept is 0. Let's just look at this again from a different angle. So if I had now, let's imagine y equals 1 over x, or some constant k over x. And I wanted to, no, let's not use that. Let's take this off. So imagine I had here, we've said A equals to K over M, which is what we were looking at. And I am not sure what my graph plotted of A against M will look like. Well, right away from here, this should able to give me an indication of whether it's going to be a straight line or not. Noting that this is the same as K times 1 over M. So what have I got on my x-axis is the question I need to ask myself. Well, I've got M on the x-axis. Yeah?
Yeah.
But hang on. This x is not if I look at this x, where this x is, and I look at where this m is under a reciprocal sign. So there is no way that these two can be mapped together. You cannot relate this to that directly because this x is not a reciprocal. It's not a 1 over x. It's an x on its own. So therefore, this means that this will be a reciprocal graph. However, if I plotted against 1 over m, now we can see that the 1 over m directly maps with the x. And that's the key thing to working these problems out. Let me give you a bit of a stretch and challenge just to see if this is kind of sinking in. Oh, even better. Let's start off with the one we just looked at. So the energy of a photon is given by Planck's constant times frequency. We're happy with that.
Yeah.
So if I plotted energy of a photon against the frequency, what would the graph look like?
A over joules. So since the that's the dependent variable in the right spots, will that just, since both the f's correlate, or like if I map it out, they both correlate to each other, will that just be a linear?
And to be more specific, you're right, a linear, but it would be a directly proportional graph. Why?
Yeah.
Always go back to this. Y equals mx plus c and map it. What do I have on the x-axis? I have f. And it's not a 1 over f, so I'm happy. They have to be in the same format on their own. So you can't have one x on top here and an m at the bottom as a reciprocal and expect that it's still going to be a straight line.
Yeah.
Good. So what's the gradient going to represent? The gradient will represent Planck's constant. But hang on, the c is on its own. This is telling me that this constant must be 0. So the place where the c represents the intercept, where it cuts. So it must cut at 0.
Yes.
There we go.
Okay, that makes sense. Yeah.
Now, if I was looking at a gas law, now you're going to do gas laws next year. So we're going to say just trying to think which one we should use here. An easier gas law. Should we use P1? Okay, we'll use that one. PV equals to nRT.
Yeah.
Pressure, volume, number of moles, molar gas constant, temperature. You're going to look at this in year 13. Don't worry about it. I'm only just throwing it in here for the purpose of seeing, can we map things onto y equals mx plus c? So let's just imagine that I kept the volume constant, I kept n constant, and I kept r constant. That's constant, that's constant, that's constant, which means you can think about them as this is 1, that's 1, and that's 1. You can even give them the same number. They are constant. They are numbers that don't change.
Yeah.
So now imagine I decide to plot a graph of pressure against temperature. What would that look like?
So
the volume of the gas is constant. The number of molecules in the gas are constant. And then you've got this other constant, which is called the molar gas constant. It doesn't change. And I decide to plot the pressure against the temperature. Bless you. In other words, here is a vessel, a solid steel vessel, and I've got a pressure gauge on it, and I'm increasing the temperature. How will the pressure vary based off this relationship?
So it seems like it would be a proportional linear line. Is there a y-intercept?
What would the y-intercept be?
Would it be 0?
Correct. We still come back to the same thing. Y equals to mx plus c. On my x, I've got t.
Yeah.
My gradient now, in this case, of course, we're assuming that we've divided by v. So my gradient now becomes nr over v.
Yes.
That is my gradient. Of course, there's nothing here to add, so it passes through 0. So it will look like this.
Yes, this makes sense.
Good. Now we're going to have a more challenging type of question here. So we're now going into waves, a little bit into waves. So the fundamental frequency of the first harmonic is given by 1 over 2L multiplied by the square root of the tension divided by mu. So this is here the fundamental frequency, or the first harmonic on a string. This here is the tension, and this value here is what we call the mass of the string. So tension in string, and this here would be the mass per unit length of the string. So the question is, I decide to do an experiment where, sorry for that, let's just, I decide to do an experiment where I vary the length of a string, and then I look at where the fundamental frequency starts. Now, fundamental frequency on a string, remember, is when you just have one I.
Yeah.
That's the fundamental frequency. So by changing the length, the fundamental frequency changes. So let's imagine I'm going to keep the tension the same. So length here is my, please note, independent variable. So what I'm changing. And then I'm measuring the frequency at which the fundamental is occurring. So this here is my dependent. I'm not changing the tension in the string, and I'm not changing the mass per unit length of the string either. What graph should I now plot so that I can have a straight line? Think about this.
Okay, so that's the reciprocal. So I need to do the dependent is, so again, F against that would have to be the reciprocal.
Have some more back shot in the corner. Right. Any thoughts?
Yeah, so the length that's been the variable, the independent variable, that's it's the reciprocal of
Good.
the independent variable.
Good.
And with the dependent variables f, so that would relate to the y. And then the x is the reciprocal.
So remember, the aim of this is, so on one side I've got my dependent,
Yeah.
my independent. So what should I choose as my independent variable so I get a straight line?
Would it be One thing that's confused me a bit is the 2L. Is that just, do I keep it as just 2? Do I keep the 2, or do I have to change
You're absolutely
that?
right. It's a good question. So this here, you can think about this again. It's just a little bit of mathematical manipulation. You can think of this as being 1 over L multiplied by 1 over 2 square root T of mu, which you can also think about, let's move that here, which can also be thought about as 1 over L. You can put this 2 in there, inside the square root sign. And what would it be if you want to put it inside the square root sign? What would you have to do to it?
If I want to put it in the square root sign.
Yeah, if you want to take it from outside the square root sign to inside the square root.
Would I have to square?
Correct.
And then that's just constant. Yeah, so it'd be the reciprocal of the x variable.
Very good. So now if I plot 1 over L over here, and I plot frequency on the other hand, I am going to get a straight line, and it has to pass through the origin.
Yeah.
And the gradient of my line, if I map it, F equals 1 over L root T over 4 mu to Y equals mx plus c. Well, this here is my x. This is my m. So the gradient of this line would be equal to the square root of T over 4 mu. And of course, there's no intercept, so it means that it would pass through 0.
Yeah.
Did we follow that okay?
Yes. Yes.
Excellent. Now there's a really good one actually. This was a really good one. How am I going to obtain it? One moment. Let me see if I can find it in my files. Because this one did puzzle. This one did puzzle quite a few year 12s in the last mock paper. These are all the latest year 13 papers. Just a moment, I must be lurking in here's end of year exam. Yes, that's it. Good. All right. Oh no, it's not that one, is it? It's the one I prepared the mark scheme for. So it's got all my solutions. Can I do it without? Okay, we can do it. We can do it. All right, I shall. Just a moment and come here.
No worries.
If I can find. Oh no, actually, come to think about it, because I prepared the paper. I'm going to have an electronic copy of this thing somewhere. So many things going on. I must say the year 12s were not happy with me. With the paper I prepared for them. I was not very popular. They all mourned. I had parents texting me and emailing me in the night going,
yeah, you could
you've
tell
traumatized them. But I said, look, that is the standard of a physics paper. I have not intentionally created something diabolical. Right, okay, so let's go here. Just one moment. Year 12. Yeah, 12 mock. I said, okay, now it's going to be one of these. What question was this? Question 2, I believe. It's going to be question 2. Questions 2 and 3. Hope it is. No, it's not. All right, okay, I'll try the next one. Hope it is. No, sorry for that. We are not winning question 1, and this is definitely question 2, isn't it? Yeah. Question 1, question 2. Right, here we go. So that's question 1 and question 2, draft 2. Okay, cool. I'll bring this forward. File and import PDF. 12. So just go here. Question 1 and question 2. There we go. And we want this at the beginning of the current flip chart. And I'll also send it through to you via the chat. So if you have to, not new share. We gotta go to chat, haven't we? Chat. Go. And so we are looking at no, there above. Yes. Yeah, 12. 12 mark. Here's 1 and 2, isn't it? I believe it is. Yeah, found it. Right, that should be making its way through to you. Okay, hopefully it's arrived.
Yeah.
Excellent. Okay, so this is the problemo, and I shall just zoom in so you can
I see it. Is it
damaging your eyes. Here we go. So a student does an experiment to determine the Young modulus of a metal. Bum, bum, bum. The horizontal distance between A and B is 3 meters. C is the midpoint. A mass of weight W is suspended at C to extend the wire. Figure 7 shows that C moves vertically downwards by a distance Y. Okay. When W is 1 Newton, Y is 6.34. I'm not going to bother with that. No problem. Calculate the tension in the wire. Again, that's just equilibrium balancing forces. I'm not going to bother with that. I am mostly interested in mapping. Okay, and it
that
is
looks fun.
standard. I know. And when they saw this, what on
Oh
earth?
my gosh, I could imagine. I could imagine.
I know it's a horrible one to see in your exams, but these are the kind of things they're going to be expecting you to have X plus C. So this is the standard or level you want to come to. Okay.
Yeah.
So a student measures that, and the next part of the question is they then want you to, I mean, you've obviously got the question. Determine E using figure 8. Determine the Young's modulus using this figure, having been given this equation.
Right. Okay. So E has to be the subject of the equation.
Just going to use the bathroom 2 seconds, yeah?
No problemo. So am I supposed to trying to sort of get it into the sort of like
Exactly. You want to know exactly what the gradient represents. You want to map this. This is the whole aim of this exercise. You want to map this onto y equals mx plus c.
Yes. Yeah, so the dependent variable should be yeah, so I kind of got it, but I don't really feel like it's in the sort of, it feels like it's a bit.
So what you always do then, you ask yourself, well, what is on the x-axis?
On the x-axis, there, that's what sort of on the x-axis,
Yeah.
y.
Yeah, but there's, look at it very carefully, not just y.
Y squared.
Good. You map it, literally mapping as in, I do that. What is on the y-axis?
W over y.
Thank you. So C, can you see there's a plus K?
Yeah.
That's mapped to the intercept.
So intercept. Yeah.
So where it crosses will be plus K. So the gradient of the straight line you're now going to draw, that gradient
Right.
this gradient now, what's that gradient going to represent?
Would it be EA over X cubed?
Correct.
Right. Oh, okay. Right, that makes, that way of doing it is much better.
Yeah.
So where is this, what
Given
paper is this question from?
Sorry?
Just so I can, what question, what paper is this question from?
This was from 2021 paper, the AS paper. It was the year 12 AS paper. It was an AQA question.
Brilliant. Yeah, just so I can reference it on my notes.
Yeah, that's fine. 2021. Yeah, November.
Brilliant. Yeah.
So no one would have seen it. That was the beauty of it. I had to get questions that definitely would not have seen. That one was not out in the public domain on any website or student room or whatever they call it. It was never there. So there you go. Once you find the gradient m, you then have to times it by x. So in other words, E is equal to m times x cubed over a. A is given, x is given, but remember to cube it.
Yeah.
Given in that expression. And to find the m, just use your largest triangle possible. And are there any tricky parts with the units? No, this is in meters square. That's fine. If this was in centimeter, you'd have had to be very careful and change the x. If you like the delta x, you'd have had to express it to the same unit as that. But there's no such trap there. They're being very kind, actually. But if they wanted to make it absolutely diabolical, they would have put this in centimeters square, but they have not in this case. Good.
Yeah.
Right. Some more mapping type. So that was that one.
Yeah, it said determine
This is a good one here. Deduce the fundamental base units for K.
Right.
What would the
Okay.
units of K be?
So would we rearrange for K firstly? Would we do that? Rearrange for K?
You could. You absolutely could.
Could, or or could you
So
just
the
look at
equation is
where it
W over Y equals EA Y squared over X cubed plus K. Now
yeah,
it's an equation. So the easiest thing to think about, if it's an equation, the units on the left-hand side
yeah,
must equal the units where?
on the other side.
Correct. It's an equation. Must equal
Right, and yeah,
on the right-hand side. What are the units on the left-hand side?
Newton meters.
Newtons per meter.
Yeah, Newton per meters, yeah.
So everything here
Newtons
must
per
have the
meter.
units of what?
Newtons per meter.
Newtons per meter.
Right, and yeah, because I was also gonna say it's on the y-intercept on the y-axis. So that's where like the value is for K. So I
Thank
guess
you.
with that also.
You are absolutely spot on. So this here,
Yeah.
if we look at this quantity, what are the units for this quantity here? Well, if you wanted to, you can quickly look at them. They must be the same as the quantity there. Or Young's modulus, what are the units for Young's modulus? It's Newton
Yeah.
per meter square multiplied by area, which is going to have units of meters square, multiplied by Y, which is also a distance, so meters square, X cubed, which is also a distance, which is going to be meters cubed.
Yeah.
So what are the units of this thing? -2 and 2 gives 0. We're using laws of indices.
Yeah.
2 minus 3 is -1. So the overall units of this thing here, I'm taking it here, by the way, is the Newton per meter, if you simplify this. So what must this therefore be? It must also be Newton per meter. But if we add them, the units don't change. The number that we've got, in terms of, I've now got 2 lots of newtons per meter, but the unit is still the same. It is still a Newton per meter.
Yeah. Okay, that makes yeah, it makes sense.
Good. And you'd also sussed it already by going, hang on, and you'd sussed it in a much more genius way. You just went, hang on, this is cutting at there. And what is the units of this thing? Newton per meter. It has to be the same as K. It has to be. Yeah. There may be other instances where you may just have to be slightly careful with manipulation, but we can cross that bridge when we get to it. So of course, now the question, so here we know that this would be in newtons per meter, but that would not get us the mark. Why?
Because are there not the fun?
Because the Newton is not fundamental.
kg meters per second squared.
What are the fundamental units of a Newton?
Kg meters per second squared.
Correct. So I'd have to take this here and then times it by m to the minus 1.
Minus 1, and then kg meters per second minus 3.
Take your time.
Oh, sorry, wait. It's minus. Oh, wait, meters. Oh, kg meters to minus 1, seconds to minus 2.
Nearly there. This m here is to the power of 1, and that's why we don't put the 1 there. Anything raised to the power of 1, same as the thing itself. So we use laws of indices. When you times powers, they have to be the same. A to the power of n times a to the power of m is a n plus m. But these things have to be the same. So I can apply laws of indices to these, the m's. They are the same. 1 add minus 1 is 0.
0.
Anything raised to the power of 0 is
1.
1.
Yeah.
Anything raised to the power of 0 is 1. In other words, these m's disappear.
Right. Yes. Okay. Makes
Yeah.
sense.
And
Yeah.
so my final answer, fundamental base units, is kg per second square.
Yeah. Normally I get caught out on the easier questions.
And it's 1 mark. It's good that they've made it only 1 mark. And in the exam, it means
Yeah.
high stakes. If you lost 1 mark, I mean, you will lose 1 mark. It's standard anyway with these exams here. Yeah. Okay. So that really is, I'm just trying to think now if I can give you another one. The rest of them are more year 13. Let's go for this one here now. The very last one, which we're going to look at, insert page. EK max is equal to HF minus phi. Now, you know this equation, so I won't tell you what these things stand for.
Yeah.
Yeah. I can also plot, say, EK max equals HC over lambda minus phi. Same thing.
Mm-hmm.
So now, if I decide to plot, or rather, what should I plot so I'm going to make this here my independent variable, and I'll make my EK max my dependent variable. So what should I plot now if I want to get a straight line equation? What would it look like?
So the independent variable, that is the reciprocal.
Very
because
good.
it's just the same as
Excellent.
doing over
And I'll put EK max there. Very good.
dependent, yeah.
Good.
Y-intercept.
This graph now pass through. Did it pass through the origin?
If we write it like that, as the would it pass through the origin? Did you say?
So take your time with this one. So again,
Did
you
you say
rewrite
would it?
out y equals
Because
m
that's the y-intercept.
plus c.
Well, since it's a negative y-intercept, then it would not pass through the
Absolutely
origin.
right. It's gonna cut at minus phi.
Yeah.
And the units of phi will be the same as the units of kinetic energy, joules.
Yes.
So whatever the units are of this thing are the units also of your intercept. There we go. It would be like this.
Yeah.
And what would the gradient now represent?
HC.
Correct. Your gradient now would represent Planck's constant multiplied by the speed of light. So if they ask you to find Planck's constant from the gradient, you need to divide that by the speed of light.
By the speed of light, yeah.
Okay, and you've got it. That is what mapping is about.
I would have had no clue how to even approach that. Not even the simplest way. I would have literally, I would have been one of the students that just write a big question mark in the middle of the page.
What's going on?
What's going on? A big frowny face.
One of my students
say you'll be getting an email from my mom.
One of my students gave me the best narrative. You just reminded me of something. Charlotte came to me and said, so I don't think I've ever told you how I actually view physics questions in an exam. And I said, how do you view them? And she wrote the question, says, all right, so imagine this is how the physics question starts off. And she says, Laura has two sparkly donuts and 3 she used some of the word vanilla flavored donuts. What is the mass of the 3 frogs? How have you gone from donuts to frogs? Exactly, sir. But when I look at a question, I go, how have they gone from that? You're talking about donuts, now you're asking me about a frog.
No, I understand, because sometimes it just has nothing to do with the
So at that point, I said, right, okay, I understand now why you found the subject quite difficult. You should have
That's
told me
good.
this
Nearly every
years
student
back.
feels
Now in
that
year
it's a
13, you're
brilliant.
telling me that I can't do anything about it. So yeah, don't worry. You're not the only one who gets puzzled. And I just wanted to say, some others even get more puzzled. You know, they see the question asking them about donuts, and then the final part suddenly says, "What's the mass of a frog?" Hang on. What's going on here? So it's good that we've gotten that understanding. I really wanted to make sure that you really understood this, and you're going to have more opportunities to really consolidate what you've learned today. So we're not going to park this and forget about it. There are going to be many questions you're going to encounter where you're going to have to deploy this.
Exactly.
All right, good stuff. But that's fine, because I'd also lined up some of the questions for us to do. Very challenging type. Ooh, how did this end up? Oh no, this was the other part of the question. Don't worry about this. We're not focusing on this. No, we're not focusing on that at all. But the questions I wanted to focus on are all included in here. Don't worry if you want us to go through them. These are, again, looking at Newton's laws of motion. They are pretty challenging, okay? We are now talking Cambridge, Oxford standard here, but they are all multiple choice. So if you do fancy having a go at these in your own spare time so that you can bring them as discussion problems next time, I'm more than happy to for you to do so. But if you want to leave them so that we actually do them together in real time, again, I'm absolutely entirely happy with that as well. Okay.
That looks good to do.
Yeah, is that okay?
Yeah,
right.
yeah.
I'm just making them a little bit big so that they are fit for use. There we go. And we're going to make that there like so. Boom. There we go. So it's a bit of a mix of different questions, but it's all topics you've done, but just on the, like I say, slightly challenging end. They're not impossible to do. They'll make you think, and they'll develop you. That's the whole point of this game here. Right. Okay, that's it. Right. Do you have any questions, Conrad? That's about it on those questions. No? Superb. Righty then. I shall. Oh, I seem to have lost you there. You've gone into freeze mode for some odd reason. Edit. Oh, I've lost you there.
Is that
Oh, better. Yeah. Good stuff. Yeah. Now I can see you. Yeah, good. Can you hear me all right?
Yeah.
Super.
I was just about to tell you.
Yeah, I know the whole freezing thing has been going on, so I think the computer's tired already. So I'll send all this work to you, okay? You're absolutely frozen, but hopefully you can hear me. And I suppose we just have to liaise over the phone when we can pick up pieces again. How does that sound? Yeah, better.
It sounds yeah.
So should we meet up? It's up to you, like I say, if you want to meet up over the weekend or if you want to meet up next week, just let me know what you prefer, Conrad.
Yeah.
Off the top of your mind, have you had a thought? Oh yeah, Thingy got in touch with me. I meant to reply to him completely, just enough time. He said he's just waiting for his parents to give him the go-ahead. But he's now at the point where he's about ready to start. So thanks for that. Good stuff. Yeah. So just let me know whether you want to pick a session up over the weekend or after the weekend. If you need more time to go through the questions, I'm absolutely flexible. Just give me advance notice and we can work things like that. Is that all right?
He definitely is ready to just lagged.
The freezing is not helping us, I know.
It's not helping.
No. But it's fine. So just get in touch if you are as and when you want your next lesson, weekend or after the weekend. I'm cool. Whatever it is that is best for you. But well done today. Really hard concepts, and you've made some good progress. That puts a smile on my face, and I hope you've got a smile on your face as well. Oh dear, it's not our day today, is it, Conrad?
Oh no.
No. Right. I wish you a good evening, man, and I'll see you soon. Cheerio.
Awesome.
Awesome. Good stuff. Bye now.